if you see, there are certain microorganisms like Clostridium, Enterobacter, Thermoanaerobacterium. So what these microbes does is that these produces enzymes called carbonic anhydrase. And these carbonic anhydrase, they react with carbon dioxide and they produce bicarbonate. So the thing is, we are not emitting CO2 in a large amount. CO2 is converted to bicarbonate in the dissolved liquid metabolites. And these are the pathways of dark fermentation. And we have just collected the data from many research papers. So our main idea is we have collected many data from various research papers, and there are plenty of data. And we have implemented our idea and we are displaying the data in the screen. So in dark fermentation, there are basically three microorganisms which is used, which are strict anaerobes. Second thing is facultative anaerobes, and the last is thermophilic microorganisms. Now let's get deep. Before that, let me start with photo dark fermentation. We just saw what is photo and what is dark. Our main motive is not just doing not doing the hydrogen process in a single step. We are basically integrating photo and dark fermentation. And if you could see, the results which we get is we would get 4 to 12 mole of hydrogen per mole of hexose. And the other thing is we could get 2 to 10 moles of hydrogen per mole of pentose. So we would get these data from integration of photo and dark fermentation. So the next thing is selection of substrate. So how do we select a substrate? A substrate could be selected by it has a basic criteria. So what are those criteria? It should be cheap, abundant, and it should have high organic matter. So we have done a lot of research, and we believe that sewage sludge satisfies all those criteria. And if you see the bar graph in that, from the year 2000 to 2016, the number of articles which has been published based on this fermentation, like we produce hydrogen from fermentation. So there are many articles, and if you see, the numbers of articles have been increasing from the year 2000 to 2016. And pre-treatment and co-fermentation. Now, why do we do pre-treatment? So basically, if we take raw sludge, it basically has a complex structures. Plus, it has some non-hydrogen producers. It consumes hydrogen. And the next thing is it has more complex things. So what we do is we basically do pre-treatment. So there are many pre-treatment, and we are proposing combined pre-treatment. So what are the combined pre-treatment? We use heat pre-treatment and chemical pre-treatment. The chemical pre-treatment which we use is oxidation pre-treatment. And you could see the data here. The thing is, when we are taking the raw sludge and when we are heating it, the hydrogen efficiency is so high. The hydrogen efficiency is so high. If you see, the hydrogen yield increase 4.6 times when we are doing alkaline heat treatment. So the point is, we are not just focusing on one pre-treatment technology. We are just doing it combined. And co-fermentation, again, the sludge basically has low C by N ratio. Like carbon to nitrogen ratio is so low. And what is the problem in this? So there are certain microorganisms which can perform fermentation only on a suitable C by N ratio. So what we basically do is we will add co-substrates. And when we add those co-substrates, that would increase the C by N ratio. And hence, we could get a higher hydrogen efficiency, and the microorganisms has a suitable fermentation process. And these are the results which we are displaying it. If you see, the co-substrate which we use is mixed sludge, and WAS is nothing but waste activated sludge. And when we are doing this, the hydrogen efficiency is maximum, and you can see those data there. And there are various microorganisms in which we use, and the three best microorganisms which we are proposing is Clostridium, which is a strict anaerobes. Strict anaerobes in the sense it works on the absence of oxygen. Second thing is facultative anaerobes. It could operate on with in the presence of oxygen or without the presence of oxygen. And the last is thermophilic microorganisms. Now, the major disadvantage in dark fermentation is that there's an enzyme called hydrogenase, and what happens is this hydrogenase is sensitive to oxygen. So the hydrogen efficiency is low in this case. And we have done many research, and what we found is when we do heat shock. So what happens is when we do heat shock, the microorganisms consumes less amount of oxygen. So the thing is we have to do heat shock. We have to maintain a higher temperature. Now that's a pre-treatment which we do, and the thermophilic microorganisms which we do here, these microorganisms can operate only on higher temperatures. So if you see heat pre-treatment, and the second thing is thermophilic microorganisms. These could increase the hydrogen efficiency. And there are certain influencing factors like temperature, pH, and solid retention time. So when we increase the temperature, the hydrogen efficiency is increased. Simultaneously, pH and retention time, these plays a major role. And now I would like to explain the reactor type. So every bioreactor has something like this. So we have an agitator where it continuously spins. So what is the use of these agitator? It basically helps to maintain uniformity over the sludge. And that's a schematic diagram of the integration of photo and dark fermentation where we get hydrogen. Okay.
Sorry, exceeded time.
Okay, this is the production method, and we have something like storage method. So what we do in storage is from this method we basically get pure hydrogen through the process called pressure sink adsorption. And from the hydrogen, how do we basically store it? So we store hydrogen in the form of ammonia. So we would have hydrogen and we react that with nitrogen and we get ammonia, and we would transport that ammonia through pipelines, and again ammonia is converted back to hydrogen. And one last thing, in dark fermentation, the byproduct which we get is organic acids. And as I said, we are using integrated form of photo and dark fermentation. Now, these byproduct which we get from dark fermentation, that can be used as a feed for the photo fermentation, because the microorganisms in photo fermentation like rhodobacteria, they consume these organic acids and they convert these organic acids to hydrogen. So when we integrate both photo and dark, we'll get higher hydrogen yield and the byproduct amount is less in amount. Thank you.
It's a good presentation. Can you just tell some challenges which you might encounter in the such process?
Some challenges are that it has optimal conditions, like parameters like temperature, pH, and all are different for photo and dark. So when we are combining both of them, under those conditions, dark has some temperatures like 37 degree to 60 degrees Celsius to fermentation, to the process of fermentation. And for photo, it is 20 to 40 degrees Celsius. And pH also differs, as dark needs acidic and photo needs neutral to alkaline pH. And there is microbial compatibility where microbes should compatible to each other. As for dark, it is obligate anaerobes, and for photo it is phototropic anaerobes, because those two are not similar microbes. They are not compatible, so they have competition for resources like nutrients and space. And light intensity also comes in play. The light distribution is also a problem. While the uniform distribution is not possible. It's not possible and difficult. and because of the depth, the intensity may decrease. These are three main challenges we face in dark and photo fermentation.
Ma'am, to be noted, the technique which we use to purify hydrogen is pressure swing absorption, and the purification is so high that we could extract hydrogen. Not only hydrogen, we could use that technology to capture CO2 also.
Always use some flow diagram and explain your procedure, because rather than theoretically telling, whether you do dark fermentation first and photo fermentation next, or vice versa, everything you put it in a flow chart and then you represent. Okay?
Okay,
Good.
Thank you, sir.
Thank you, sir.
You were talking about the sewage sludge composition, right? Which
Yes.
was leading in the hydrogen production. So, what are the major component? Have you analyzed that?
Yeah, it's like 20 to 30% of it is carbohydrates. The thing is, we'll have 40 to 50% of organic matter. But even there are classifications under organic matter, which could be carbohydrates, proteins, lipids. Among that, 10 to 30% is carbohydrates, and the remaining is lipids and proteins. And we do have traces of heavy metals, and even we have a data here which we are sure. I think okay. The thing is, if we have a more amount of heavy metal, that could decrease the efficiency. But when we are using it in the trace amount, it has resulted that the hydrogen efficiency is increased.
Okay.
Ma'am, can we give a short note on the storage, ma'am? Thank you, ma'am.
Thank you, Arsen, Hassan, and Leon. For the next presentation, I would like to call S. Sushidharan, S. Prakadesh, and S. K. Venkataraman from the Department of Chemical Engineering, St. Joseph's College of Engineering, to present their paper on cutting edge technologies for biohydrogen production and sustainable storage solutions.
Good afternoon, everyone. I am Mangatraman from St. Joseph College of Engineering. Today, we are going to see about the cutting edge technologies for biohydrogen production and sustainable storage solution. We all know that energy is the important source for the country development and everything. It has been predicted that consumption of energy will be going to increase 35% while we are going to reach. Introduction. Increasing energy supply is required by the sustained economic development. It has been predicted that energy energy supply is going to be increased from 2024 to 2035. 80% of the energy we are depending upon the fossil fuels for everything. But usage of fossil fuels, usage of fuel is a danger for our environment. It may increase the global warming, acid rain. It may cause us some of the demerits. So we are advisable to use the renewable energy as the alternate source of fuel. Because of the high calorific value, hydrogen is used as the alternative fuel source.
And in this review, we have taken three types of feedstock for our comparison for the different types of production of hydrogen. First one is agriculture residue, and second one is algae, and third one is waste activated sludge. And we have taken three types of biological process for the production of biohydrogen, because gaseous process can produce hydrocarbons in the process of production of biohydrogen. So it is not for good for sustainable development. So we only consider the three types of biological process. And first one is dark fermentation. In the dark fermentation, we will use some bacteria to convert a feedstocks, or that means a biomass, to produce hydrogen and organic acids. And in photo fermentation, this is the same process like dark fermentation, but it has some extra sunlight for the production of biohydrogen. And there was we used the three types of feedstock for the production of biohydrogen, and we have compared. And the last one is microbial electrolysis, and in this we use like an electrolysis based thing, which will use the biomass as a fuel, and we produce the high biohydrogen. The biohydrogen will be stored in the cathode. And advantages of biocatalyst. Usage of biocatalyst is like in adding the biocatalyst in the feedstocks will increase the biohydrogen production, which will increases our efficiency of our system, and which will also increases the yield for the biohydrogen. And genetic engineering in the enhanced production. Genetic engineering is the thing which increases the carbohydrate content. The carbohydrate content in the biomass is the main part for the production of biohydrogen. So by increasing the carbohydrate content in the bacteria or in the feedstock, will increases the efficiency of our system by increasing biohydrogen production. And next one is storage. The main challenges, the challenges in the hydrogen storages are low energy density and high pressure or low temperature requirement. And because the hydrogen can be only stored in a high pressure due to its nature. And third one is a safety concern. And hydrogen is an odorless and a colorless substance, which will be a very challenging thing for a storage, and it's have many safety issues. And then storage materials. The storage materials are also a really challenging thing for and then is cost. And that the major types for storaging for the hydrogens are compressed gas storage. In the compressed gas storages, the volume of the hydrogen will be decreased and it will be stored. It will be helpful to the then it will increases the density of the hydrogen, and in majority of the cases compressed gas storages are used for the small scale productions. And in liquid hydrogen storage, the biohydrogen is stored in the form of liquid, and by decreasing the temperature, and it will be stored as a liquid, and it is used for the long storages. That means a large amount of hydrogen can be stored as a liquid hydrogen. In majority of the cases, the submarines and ships are using liquid hydrogen. Even rocket fuels are also stored as a liquid hydrogen. There one is now newly emerging technology, the solid state hydrogen, which will be the hydrogen will be stored as a solid. The main types of solid state hydrogens are metal hydrates. In metal hydrates, the chemical bonds will be the hydrogen will be the hydrogen will be in the material. By heating the material, the hydrogen will be produced, and then sodium borohydrates are also example of metal hydrates.
This is the data that collected from various papers, various review papers and research papers, that dark fermentation gives energy conversion rate as 4.3, and the higher will be microbial electrolysis cell, that will be 11.3%. So we can conclude that microbial electrolysis cell will be more efficient. We can conclude that microbial electrolysis cell will be more efficient when compared to photofermentation and dark fermentation, where dark fermentation shows 4.3 and photofermentation shows 5.1. While doing microbial electrolysis process, it will be more efficient and gives also clean water, and activated sludge will be more efficient to this. Thank you.
It was a good presentation. Can you tell me about the microbial composition consortium, basically? The microbial consortium.
In microbial electrolysis cell, we can use VAST, that means waste activated sludge. It will produce more efficiency biohydrogen, and we can also get free effluent water, that means pure treated water.
Can you name those microorganisms that have been used there?
Microorganism used for microbial.
Rhadomicrobium velini, purple bacteria.
Okay, is it a mixed one? Do you use mixed ones or only single color?
We can use both ways, ma'am. It depends upon the efficiency.
What about the economy?
While considering economy, we can use renewable energy for microbial electrolysis cell, ma'am. So we can reduce the economy also. If we use the without renewable energy, the economy will be high. But if we use renewable energy, we can reduce the economy also. So it will be profitable.
Okay. Okay, pa. Thank you.
Thank you. Please hurry up.
Thank you for the presentation. Next, we would like to call Meghnathan Kurularasan Harish from SRM William I. Engineering College to present their paper on technologies for biohydrogen production and storage.
The same day last volunteer. On பண்ணிட்டா இது அலாரம் இருக்கும் சவுண்ட் வரும் see you get an alarm sound at 5 minutes okay please wrap it up by the time.
Good afternoon, everyone. Myself, Purla Sanyas, Meganathan, and Harish. We are here to present our paper presentation on technologies on production of biohydrogen and storage. These are the topic we're going to see. Introduction: biological hydrogen production through process like biophotolysis, dark and photofermentation, and the biocatalysis electrolysis. The significant advantage of the over thermochemical and electrochemical method. Storing biohydrogen is the challenging, but crucially for a sustainable hydrogen economy, the key method of the compressed liquid and the material-based storage. This is the pictorial representation of the production, storage, delivery, and end user. Biohydrogen production. To generate hydrogen gas from the organic materials, fermentation and photosynthesis. The main three topics of the photolysis in microalgae, fermentation, and the electrochemical process.
And these are the common methods that used to produce biohydrogen using biological process, such as biophotolysis, fermentation, and electrochemical. In photolysis, there are two types, that is direct photolysis and indirect photolysis. As they said, direct photolysis uses sunlight to segregate hydrogen and oxygen from water molecule using microorganism, and indirect is vice versa, that absence of that converts water and carbon dioxide in carbohydrates, and it converts it into hydrogen. In photofermentation, and they use sunlight and microorganism using anaerobic digestion, and they produce hydrogen. And in dark fermentation, absence of light. And in photoelectrochemical, they use sunlight and the microorganism and electrolysis process to produce hydrogen. And electrolysis process use a normal method uses cathode and anode process. And next is production of biohydrogen from organic waste. As CBCB, Central Pollution Control Board of India, has conducted a survey and released an article on 2020-23 and states that 1.6 lakhs of ton per day of solid organic waste are produced. From that, 95% of the waste are collected, 50% of waste are treated, and 18.4% waste are landfill. That remaining 30% are remain as unaccounted. From the research and study, we can use that 30% of waste, such as food waste, wastewater, treated wastewater, that can be used to produce hydrogen, biohydrogen, and waste such as wastewater, food waste, and cellular-based waste, starch-based waste can be used. Food wastewater. Once the water from municipal waste that are treated means it removal of heavy metals and inorganic compounds can be used for the production of biohydrogen. If by adding inoculum method, such as adding algae and using photolysis process, we can produce hydrogen. Then food waste can be pre-treatment, such as mechanical method, physical method, that can be used for homogenization, to making the products to decompose fast, quicker, ferment faster. These conditions are made in mesophilic condition, such as moderate temperature of 20 to 35 degrees Celsius. Next is cellular-based biomass. These biomass are conventional method, the use of sugarcane waste and other agriculture waste. The starch-based are tapioca, potatoes, that are used as the raw material. And these are the challenges that is based on the methods that are used.
biophotolysis, as it produces, it requires oxygen generation and low light conversion. Indirect photolysis, high light conversion and low hydrogen yield. Photofermentation requires low high conversion efficiency, required external light. Once the usage of sunlight is over, we need to produce, we need to give external light for these methods. Dark fermentation, thermodynamic limitations, required separation of hydrogen and carbon dioxide. Sequential method combined system, combine different good condition of DL bacteria, pH drop and accumulation. To overcome these challenges, we can use integrated methods such as combination of dark and light fermentation, or usage of two-step combination, three-step combination methods that can be used. And next is storage of hydrogen. Conclusion. From the study, we can state that the usage of biohydrogen can decrease the production of pollution, and we can use the waste produced by us to convert the waste into sustainable way, like production of biohydrogen, and the byproducts which is produced after the production of biohydrogen can be used as the manure or other usage such as agriculture manure, and the water that is treated and produced biohydrogen can be used as the irrigation waters. That's all, ma'am. And the storage, that should be told and finished.
The presentation was well. We are talking about different types of production methods, right? What
Yes.
is that carbon monoxide gas fermentation method? What is feedstock for that?
That actually we have to study, ma'am. We took only 4 main methods. That's came challenges.
Okay, you're talking about municipal solid
Ah,
waste to yield a high amount of hydrogen. So what would be the major composition of municipal solid waste that you are considering?
Ma'am, the municipal waste can be contained of food waste, kitchen waste, organic waste that can include agriculture waste, and the sewage that are produced. Once the produced sewage can be separated with help of primary method in normal municipal waste, ma'am. Once the water is separated, that these water can be used for biohydrogen production, ma'am.
Okay.
Of all the methods you mentioned, which will be the most cost effective and reasonable?
In spite of using wastewater, we can use biophotolysis method, ma'am. As the water, we are going to use water and lesser solids. The usage of algae can be effective, ma'am. Photosynthetic algae, cyanobacteria, and chlamydomonas that is used in biophotolysis can be effective in both treating the water and production of biohydrogen.
Okay, good, thank you.
Next, I would like to call upon Artana CR, Anusha Ramamurthy, and Bala Sundareshan from Sri Venkateshwara College of Engineering to present their paper on production of biofuel using zirconium oxide, titanium oxide, and nanocomposites from waste cooking oil.
Okay, good afternoon. So we are presenting a paper on the production of biofuel using chitosan-based zirconium dioxide and titanium dioxide nanocomposites from waste cooking oil. Now, traditional methods of producing biofuel and the catalyst used in process often result in low conversion rates and suboptimal fuel quality. So we decided to investigate the use of chitosan-based titanium dioxide and zirconium dioxide nanocomposites. Now for the methodology, we collect waste cooking oil and it undergoes pre-treatment like filtration to remove impurities and dehydration to remove the water content. Then for the synthesis of zirconium dioxide and titanium dioxide nanocomposites, we use sol gel method, or you can also use hydrothermal method. So chitosan is a natural biopolymer which is derived from chitin, which is found in crustacean shells. So it is mixed with acetic acid to form a uniform solution. And then now zirconium dioxide and titanium dioxide, they are formed using sol gel method, and then they are dried and calcinated, and then they are mixed with the chitosan base using mixing, or like by stirring vigorously, or using sonification, which is subjecting it to ultrasonic waves. Then these nanoparticles are characterized using FTI, which stands for Fourier transform infrared spectroscopy, which helps in confirming chemical bonds and identifying functional groups. Then we use X-ray diffraction for determining the phase, purity, or the crystalline structure. And then we use transmission electron microscopy for like surface morphology. Okay. Then after now, in a reactor, we use the waste cooking oil as a feedstock, and the catalysts are the ones which we synthesize, which is the zirconium dioxide and titanium dioxide nanocomposites. Then this reactor is heated at 300 degrees Celsius to 400 degrees Celsius, which is like the optimal temperature range for decomposition of the waste cooking oil. The catalyst to oil ratio is used is 0.7 percentage to 0.8 percentage, and the time taken is 120 to 180 minutes. So under high temperature, the chemical reactions in the reactor lead to the production of biofuel, oil, and then syngas, which is a mixture of carbon monoxide, methane, and other light hydrocarbons, and which is a char, which is a solid residue, which is often reduced while using catalysts.
So the observation confirmed the X-ray diffraction confirmed the analysis by showing the crystalline anatase structure of titanium dioxide, and also its mesoporous structure, which plays a huge role in the interaction between the feedstock and the catalyst. And the high surface area is also very important in production of yield, in production of high quality yield. The results confirmed the optimal temperature, optimal weight, and the optimal time for the catalytic efficiency. The test during the pyrolysis of phase cooking oil, the optimized conditions are temperature between 300 degrees Celsius to 400 degrees Celsius. The catalyst weight has to be between 0.7 to 0.8 percentage, and reaction time should be vary between 120 to 180 minutes. So the perfect condition is around 350 degrees Celsius and 0.75 percentage, and the time has to be between 130 minutes. It shows better. It shows better. But it shows better property during high surface area and its mesoporous structure, and also we get proper conversion rates by during in these conditions.
So the application of this in day-to-day life would be taking a scope to the small-scale biofuel production units, meaning there are many biofuel production units in rural areas. So we want to set up a decentralized units which need a minimal amount of biofuel. So and then we have a circular economy and waste to energy solutions, which means we would be deriving the waste from seafoods, seafood derived waste such as shells and shrimps. So from which we'll be converting into valuable biofuels, and then carbon capture integrated biofuel systems, which
Please, can
means
you go to the conclusion time up?
So the conclusion would be we would be offering this methodology would be offering we'll be using chitosan based ZrO2 and or TiO2 nano composites, which basically enhances the surface area, metal oxide dispersion, and the number of active areas. And this will be also enhancing the efficiency, reusability, and potential for commercial applications.
It's a good presentation. Can you tell me about the FFA of a waste cooking oil? FFA percentage, free fatty acid percentage.
Basically, we have been doing this in a lab on a lab scale, so we are expecting it to take it onto a industrial scope. So
Whenever you present, at least some of the physical characteristics. So waste cooking oil is sticky, but whereas the produced biofuel is non-sticky. Like that, even though you're not going for chemical or any doable experiment, at least physical observation, the color is so thick. It is like that, again, flammability, the oil it takes long time to get flammable, it quickly flammable. Like that, some characteristics you have to present. Okay, then only it will be. That is why you are producing waste cooking oil to the biofuel. So what is that characteristics you are going to differentiate? You have to give it in maybe a slide or at least in tabular format. You have to give it. Again, I presume you are using this zirconium and titanium oxide for absorbing the pollutant which are present in the cooking oil, so that it converts the biofuel, isn't it? Again, what is that absorption taking place? That also to be mentioned. Okay. Good.
Next, I would like to call upon Vidya Sagar A, Chinnadevan S, from SRM Willamay Engineering College to present their paper on process for sustainable bioethanol and biohydrogen production.